Okay, let's get going. So Steve, be able to spend any more time on brain tumor stuff?
Yeah, like I've had a bit of time this week, so I've just been sort of working my way through some of the EDA notebooks and like through some of the discussion things and stuff, just to get up to speed with the competition, really. So yeah, like there's a few I've seen. I'll share my screen here, and I've just got bits and pieces, like so. Um, yeah, so unfortunately I've got too many tabs again. I don't know where everything's gone. Yeah. Yeah, like just within within the discussions, there's quite a few good things. Let me just find where it was. Oh yeah, so yeah, so like I'd basically just like sorted these by most votes or whatever, and was working my way through some of them. I noticed that they've just put this thing in, saying that there's 3 of the cases in their training samples that should be excluded. So I haven't got around to taking them out yet. This one here I'd posted a link to already. It's like somebody who's converted all of the DICOM images into PNGs. So yeah, like it's dropped from 128 gig down to just over 5, which means then like I was able to take these and put them into Colab. And then the other one I was looking at, this thing here, this compilation. Yeah, so this is just like 9 different notebooks or whatever. So I'd worked my way just taking a look at like the 9 of these. There's a couple which are actually sort of attempts at making submission files. Some of them are a bit random in how they do it. Like, yeah, this one here. So like, yeah, there's the 4 different types of MRI. All he does is basically he picks one from each set at random and sticks them through a CNN, which is a bit, yeah, it's fine for like a baseline thing. Obviously, it's not going to give you the best scores. And then like this one here, he does something similar, but he takes them from like the middle of the images. So yeah, he's getting sort of pictures from the big brain rather than from the sides of the brain where you might not have any image at all. There's another one here as well. Yeah, like this one here. He just like mentions loads and loads of like different papers related to the thing, and like just describes all the images and describes like a stack of papers to do with sort of dealing with DICOM images and how you can progress on it. So it was quite good. So like then, as I said, been able to take the PNG images, so taking them over and just stuck them into Colab. Yeah, like just looked at some of the images. Yeah, so like one thing I noticed is even in the DICOM images, when it's like the full brain being shown, you can see here there's like massive amount of padding around the outside. So there's more padding than actual brain image. So yeah, like I just like taken some code or whatever, which converts that into these, so it gets rid of the padding. And like there's other people who have done, so like there's people who've like done animations on it. So I'd taken some of that stuff. Yeah, so like once I was able to get rid of the padding, I was able to get like the full image. And then so you can see here, these are some animations from it. So the top one is before the padding's been removed, and the bottom one here is with the padding removed. So you can see like now all that's contained within the image is like the full. I had to drop the size down, so the resolution's maybe not quite as good, but like that's just for the animation. But you can see, yeah, like if you were to put this into CNN or whatever, you've got a complete picture of a brain as opposed to just a brain that's small compared to the rest of the image. And then, like, apart from that, yeah, I'd just been sort of taking some code and, yeah, sort of making up, yeah, like a Git repository of some code to handle this stuff. And then with the Git repository, I can like then put that into Kaggle. And like from that, then, yeah, like I'm able to just like create the images without having to like put massive amounts of code in, because it was like finding every time I wanted to like load a DICOM image, I had to copy big chunks of codes. So that's about as far as I've got at the minute. There was one other discussion thing that I saw was, if I can get back to wherever it was. Yeah, in the discussions, the other thing I noticed was that this competition is actually split into two different bits. There's like the bit that's within Kaggle that we're looking at, but then there's another half to the competition, which is mentioned in here somewhere. Oh yeah, here, using data from task one. There's like another competition that's running at the minute, which is to do with exactly the same data, I think. But what they're doing here is like the segmentation of the code. And yeah, like looking at like sort of what we're trying to evaluate here, we're trying to like look at the tumors and decide if they've got like the MGMT thing on them. Perhaps like you may need to do this in parallel or whatever, where you sort of use something like the segmentation type thing to identify the tumor, to like then only use those bits of the images to decide if there's MGMT or whatever on it. And like this part of the competition here, it sounds more like what the previous year's competitions have been. So, but I haven't looked into this that much. But so
yeah, so I spent similar to you. I spent a lot of time that I'll go over some of my findings. I haven't yet, unfortunately, kind of played with the code yet. I just wanted to kind of get myself oriented back with the whole medical imaging field, and I jotted down a bunch of questions for Mehul, since he has experience in that domain. But then in the process, I was able to answer many of them myself. So with respect to what you mentioned, Steve, about this other competition, yeah, I saw that too. But a couple of comments about that. One is, yeah, that competition seems to be one where the desire is to segment the portion of the brain that has the tumor. So that's the segmentation challenge, which is there. Now, two comments that I thought were very interesting once you dived into further following up on what that guy said. There were other comments in the comment to what he had posted. Part one is apparently that, in order to do the segmentation, though, you'll need segmentation mass in your training. And right, so if the data were identical, then we could just borrow the data from there and use that here. Unfortunately, and I haven't double clicked on it or double checked whether the statement is true, but a couple of people commented that the data in that competition is not the same as what we have. And because of that, it's not a simple matter of importing that data and using it for our competition. You see what I'm saying? So the segmentation, in order to use that data to identify the location of the brain tumor and segment it, we'll need segmentation mass. But the segmentation mass in that competition cannot be used directly with our data because the data is different. So, or at least that's what a couple of people claim. So, I don't know whether anybody will do it, but one of the people commenting on it said, well, I mean, it's just a matter of taking the time to say, to do hand segment the images we have. Now, obviously, that's not a trivial task, but I don't know whether anybody would, it wouldn't shock me, but it would require quite some work to provide the segmentation mask or the data we have, which in fact is related to one particular question that I had, because, obviously, being far away from a physician, the question I had, it may seem like a very stupid question, but I wanted to check the assumption whether the MGMT promoter, which we are trying to predict, is actually only present in the portion of the brain which has the tumor, or is it something that we can, our other portions of the brain also have things that indicate, the non-tumor portions of the brain scans, do they have any indication, or would they be able to indicate anything having to do with the presence or absence of MGMT? And it turns out, if you dig into it a little bit, that that was one of the questions I had, and it turns out that the MGMT promoter thing, or methylation, or whatever that detail that we're trying to predict, is only in the portion of the brain that has a tumor.
Yeah, that's what I thought as well.
Right. So
that's why I thought that, yeah, we would need to, or if you were able to identify which images have the tumor, like using sort of the segmentation techniques, then it would hopefully give you like an advantage in terms of predicting the MGMT presence.
Right. But now, one thing I would correct you, though, with respect to what you just said, is the other thing I found out in the process of digging through the comments. Basically, as I said, I spent the time kind of just wanting to understand what people have done or what the data is and that kind of stuff. And the portion that I wanted to correct, or that I understood, is each of the 585 images actually does have a tumor. So it's not that they don't have, that any of them do not have. All of our patients that have data in this competition do have tumors. So there is none without, but where it's still the segmentation can help is only, just like you showed, right? There's a lot of padding and you can get rid of the padding. But even within the brain, you could potentially only segment the portion of the brain which has the tumor, or the tumorous part of the brain, so to speak, and use that and only that as a predictor. Now, unfortunately, the problem with that approach is we don't have the segmentation mass corresponding to where the location of the tumor is in our training data. And as I mentioned, the problem of, we can just get it from the other competition is, at least to first order, and I haven't verified this part myself, but a couple of people commented about it, that data and this data doesn't match. The patients, as identified by the numbers, are in the same, and apparently the image data is in the same either. So that puts a kibosh on using that data to kind of get the segmentation mask, so we can extract the tumor within the brain and then use that to, and only that portion of the image, much like you showed with removal of padding and focusing down on the brain, we can focus even further within the brain in only the tumor part, and you can't do that right now because of the lack of segmentation data available. But somebody was saying, it's not that hard, and in fact, he referred, I bookmarked it somewhere, but there's simple tools to apparently create segment mass by humans looking at this stuff.
Yeah. Do you think it matters, though, that you're not actually sort of able to create your segmentation model from this training data. Like say you created like a segmentation model from any other data from previous year's competition or from that second part of this competition. So you create like a model that can identify the tumors, and then you can run it on like the training data from this competition.
Oh, but that's
like
the
it's
point,
all
right? In order to train, it's all MRI data, but in order to train your model to be able to predict where the tumor is, you'll need it to learn by giving it examples of where tumor is, right?
Yeah, so you would train it on different data, and then you would apply it to this data.
Yeah, and you know, don't know, at least the couple of people who commented, and I don't know, you know, the expertise of anybody in this, but they seem to think that if you trained on different data and used it here, it may not, but it wouldn't work, and you needed the segmentation mask for the data that you were working with. But that's a good question, whether you can just train it on certain brain images with segmentation mask and then just use that to see whether you can predict the segmentation mask for the current set of images, and then as a second step, using that prediction to then predict what we are trying to predict.
Yeah, I didn't look at that segmentation competition, but if the data is like, you know, if they also have like T1 and flare, if it's like the same type of data, if it's different subjects, what Steve said should work. Like, and we do that all the time. For example, for like some liver MRI and spleen MRI, like we have just training data from one trial, and then we apply, you know, we train a model and then apply it to another. But the assumption is the acquisition is the same. So it is 3D T1 or T2 or flare. But that's one thing. The second thing I was thinking about is, you know, I haven't seen it in brain tumors, but there's something else like called lesions, right? So many times what happens is there might be like a, you know, there's a lesion probability map or there is a tumor probability map. Like if you have MGTM, if you have the promoter, maybe it's more frequent in certain areas of the brain than not. And even if it, so that might be worth just doing the cropping and having the whole brain, and then seeing where the tumors occur in the brain, like in the front or the back, or they're basically just four lobes. So where they occur, that might help the model. But yeah, I don't know. Yeah, those are just two thoughts that came up while you guys mentioned the.
When I was looking at the, I haven't like sort of delved deeply into the other half of this competition, but I'm pretty sure like in the discussion, the first person had said that it was the same data set, but it was a reduced version of it. So I do think that it does have like the flare and the T1 or whatever they're called. So I do think it has the same sort of set of images, if maybe not exactly all a complete match for our part of the competition. So
yeah, if they only have flare and T1, then we train only on flare and T1, and then even when we apply, we only apply on flare and T1. Segment. I think.
Go
ahead.
Go ahead, Mel.
I was still looking for like I saw the PNG images there of there's one notebook which is like saying connecting voxel spaces. Yeah, so it's like, you know, the same voxel. It's the same. Wait, I can just share my screen. But we said we could. Do you see this notebook?
Yep.
Okay, so this is the same person, the same subject, but there is the first one is the T2 weighted and the second one is the T1 weighted. And see, then when this was acquired in the sagittal or the sagittal, and this is in the axial, right? Then he just goes about. Um, there are some open source libraries. So one of the most popular one is ITK. Um, so what he's done is he just converted. So DICOM is like one slice. One image is one slice of the brain. So there's a format called Nifty. So he just converted it into basically then it's one image, but it has all the slices of the brain. Okay, so he's converted it into that, and after that he's just showing how to um, mm, resolve this problem. Like, but last time we had talked just for everyone's reference. So last time we talked about Srinivas has a good idea that hey, if they are different orientations, we can just have a model for T1 and a separate model for T2. So you don't have to put all of them in one model. Um, so instead of
Mehul, on that.
yeah, go ahead.
Sorry, go ahead, finish.
Yeah, and so if you have RGB, so instead of RGB, you can think of T1, T2, and flare, right? Like being your channels. So you can make your channels whatever you want, but if you want to do that, then you have this problem of registration, and I think he just shows how to register, yeah, and then finally now both of them are in the same like orientation. So a voxel here is it's the same position. Yeah, that's all I had. Yeah.
I take it you can't do
Yeah,
that
no,
when it's one of them's a side view of the brain and one of them's a top view of the brain.
You can still do that. You just have to convert it. So that's what he did. Uh, so he so you do something called
I can see when you got like the T1 and the T, is it the T1 and the T2 or just whatever you call it, like top to
yeah,
bottom.
yeah.
I can see how you could put those together, but yeah, those two there, how can you put those together?
Yeah, so what he did is so this data, if this is basically a matrix, right?
Yeah.
When you shift dimensions of a matrix, it will if you
All right. Yeah. Sorry. With you. Yeah. Yeah.
yeah. So if you shift the dimension, you will eventually get into this view. So
Yep.
the same, and now the problem is like, so you can shift the dimensions, get it into the same view, but now you see this one is 256 and this is 512. So I think he probably did some more stuff to yeah to match them. It is the last one. So then they are both 512. So then you can say like okay this you can actually see it. So this part it's not perfect, but this is like water in the brain. So this position and this position is roughly like now aligned, and this is like it's like a valley, the black thing here, and it's not perfect, but they are pretty close. Okay. Yeah.
Um,
um,
the the image format you mentioned there, the Nifty or whatever it's called,
Yeah.
is there an advantage to using that over having just
Um,
PNG set
I
of?
I mostly I think PNG might be fine. It's just like you will have 512 PNG, right? Here you
Yeah.
will just have one Nifty, but the I can look how to. I think no one has created a Nifty data set. Maybe I should do that and just share it on the challenge. So
I think people have, although I
they
don't know
already have.
whether they have posted it, they are using it in their own notebooks.
They are using it. Yeah.
Yeah, I saw people using Nifty, but which leads me, by the way, sorry, did you have more to say? And then I
Yeah,
can talk
just
about
one more thing was so the advantage, maybe the only advantage of Nifty is like so there is there's this network called it's a PyTorch based network for AI. it's supported by, I think, King's College London and NVIDIA. So basically, they have some tools like they have a 3D classification. Medness, yeah, maybe no, that's the 2D one. So this one will take Nifties and do your training, whether it's 2D or 3D. So you can use like this PyTorch if you prefer PyTorch. I was just trying to see if I can find. I remember seeing.
There is an MNL net. I have a bunch of bookmarks I can share later, which points to a whole lot of 3D pre-trained networks related that you can pre-trained even on 3D, but you know that I'll post links to once we're done. That potential. I mean, I haven't started using it, but I just wanted to identify that kind of. There is something called MNL net, I think, or something, and I can.
I see. Okay.
Which is pre-trained on 3D data on CT scans primarily, I think, but also on. And then there are ResNet 3D, ResNet 50 3D, ResNet 34 3D, and those kinds of stuff.
Yeah. So I think that's a great. Sorry, that's a great point. So one thing, okay, I saw at work recently is. They've been doing some CT classifications. Okay, so we have 3D CTs, and I have in our competition we have 2 classes, but in my CT dataset we have 10 classes. So one of the things we hired a new engineer like last year, and in the past we've been using like pre-trained networks with so all of them have like ResNet 50 as 50, and then ResNet whatever 100 as 100, right? And one thing he came up with is he's like that these medical tasks are not so hard. So we don't need that many layers. So the most recent project we did, he just has like 16 layers. Like it's not even pre-trained. He just has like a four dense blocks, and each block has 4 layers. So 4 into 4, 16, and then a global average pooling layer at the end. And it works. I'm just surprised how well it works compared to having and then I was like, how come this just 10 to 15 layers work? And the one thing we noticed different is like if we use 100 layers, the training goes up very fast. Like by the second epoch, it's like 85, and then it's just stuck at 85, 86. With the fewer layers, it takes more time, but eventually it just gets there. But we should, but it'll be very interesting to see whether have a pre-trained network or just train a smaller network from scratch. I think that will be like an open question. What I want,
and you could also, if you're training from scratch, you could do the other thing related to what Steve was showing us is you could reduce the image size and do what FastAI calls progressive resizing. So you could train with a small network with small images and then increase the size of the images.
I see.
As you train from scratch. If you're training from scratch.
Okay, I see. Oh, sounds good. Yeah.
Right. Before we move off this topic though of orientation and stuff, the comment I wanted to make and the thing I wanted to highlight, and maybe it lead to a question too. Originally, it led me to, or I had a question, which is what led me to this answer, which then raises, as with these things, yet another set of questions, which is an open question we can discuss. So the first point is, I think maybe you explained last week about how these images can have 3 different orientations, right? And again, I'll post whatever I think link to what those are. But basically, they are the 3 planes, right? You can look at the brain bottom up, which is the
I'm just trying to
Yeah, go ahead and pull the whatever reference link up. But that's the axial view, and then the sagittal view is from the side, that is from the ears looking in. And then there is the coronal view, which is from the front or back, that is from your nose going back, right? So those are the three different views that you can have for any MRI scan. Now, the question that prompted, or the question that popped into my head is, we have 4 types of MRIs, right? So the question I had, and the discussions immediately answered the question, and in fact, somebody had identified it and has a notebook which classifies and puts it in the CSV, is the following. At least for each type of MRI, are the scans all of the same orientation? And the answer is no. The answer is no, which in itself is somewhat troubling, right? Meaning, let's stick with FLAIR for an example. So not all the FLAIR images of all the patients are taken with the same orientation. So which means if you are even trying to learn from the FLAIR data, right? You still have the problem that, or at least your network is being put at somewhat difficult situation of having to learn from images that are all of different orientation. So I was wondering whether there is any good, and I haven't now, which then, since that data exists, of which image is of what orientation, or which group of images, I should say, right? Because every MRI scan is obviously certain number of images thick, meaning in the depth dimensions, right? But so I should always, so one should always understand that when we talk of FLAIR, or stick with FLAIR for a minute, which is one type of MRI image, then that itself is a 2D image with some level of depth, but with orientation being different. So the question that comes up, Mehul, is there a smart way to handle this different orientation? Now, one way is this nifty way that you mentioned, right? If you can convert every FLAIR image into a nifty, I'm assuming something about nifty, but again, I haven't dived into this part in detail. That was among the next steps that I was going to take, is understand whether nifty allows you to go from, if you can take an image, FLAIR image, and convert it to a nifty, then if nifty allows you to change orientation, right, then I would think the preferred approach is for every FLAIR image for every patient to take it to nifty and make the orientation the same and then learn.
Yeah, I think.
You see what I'm saying?
Yeah, no, absolutely. Yeah, so you want, like, let's say we want all the flares to be axial like this. Yeah, that, because if you try to, like I think you're right. We need to get them in the same orientation. Yeah, you give like 80% axial and 20% sagittal. It looks completely different, right? Yeah, nifty is one way to get it into the same orientation. I'm trying to see if.
But I don't know whether that works, because again, this is something that I had as next steps to take on my list. Is some people commented that whichever, and first of all, I don't know whether nifty is the way to convert, but the other comment that people had, which I needed to dive into details, is they were saying that you can only convert successfully from one orientation to another orientation if the thickness of your slices is within like a particular, there's a limit to the thickness. If it's too thick, that is, your images are too far apart, you can't really go from one orientation to another orientation very successfully. That intuitively makes sense to me, because all you're saying is, you can't really get a different picture if the thickness of your image slices is not very good in one orientation, because then successfully turning the orientation and trying to generate the pixel, you're interpolating too much. And that does seem to intuitively make sense, but I just wanted to get your take on it, whether what I'm saying makes sense.
Yeah, yeah. If sometimes what we see is like in the X and Y, the resolution will be like 1 millimeter, 1 millimeter, and then in the Z, the resolution is 5 millimeters. It's because they can only, yeah, the patient can only be in the scanner for so much time, and so they can't do a very fine scan on the Z. So you will sometimes see that this is probably like this image was 1 by 1 by 1, so it looks so nice in all the orientations. But if one orientation is bad, it might, it might look blurry here. um, Let me see. And some, yeah, I don't know if, okay, so yeah, even, okay, so is it like, okay, if the slice thickness is a lot, what I don't know is like, okay, I think it's still better to bring it to one orientation, rather than keep different orientations. Um,
Because I think at least from my understanding, I haven't seen, I haven't looked at every submission so far, but couple three that I looked at, which correspond to the ones that Steve pointed to, like the top baseline notebooks. Obviously, I didn't look at the top results and stuff. I just looked at the um, baseline starting kind of thing that uh, Steve's list pointed to, and those ones, yeah, was obviously because they're baseline oriented, they did none of this, and so I was just curious whether and they did amazingly simple things, right? Like as Steve pointed out, they just took. I mean, I've seen two or three different variants, and I think a couple that Steve alluded to. One is just taking a single slice from every not orientation, but from every type of MRI image, and then converting that slice, and it's even a slice in the middle or some random slice. So first of all, there are four types. So you take one random image from each of, for a given patient, you take a random image from each of the four types, not even at the same dimension or the same. I mean, obviously you make them the same dimension, but what I mean is it's not the same slice. It's a different, whatever, random slice. And then you make it into a 4-channel image, or in another instance, I think in one instance, the guy just taken 3 of the 4 types and made it into a 3-channel 3D. Once you make it into 3-channel, you don't even need to go to 3D. Just make those channels and you use a 2D stuff and run 2D convolution on it and submit it. I don't know how, I don't know the score for that, but that is as simple gets, right? Meaning
yeah.
you just take each of the types, 3 of the 4 types, make them the same size, convert or pick a random slice, and then run it through a convolution model predict. The other thing which amazingly has gotten a score of 0.6 something is, another person approach something similar with just combining the slices, and which is what I was amazed at once I learned that the orientation is not even the same. You take, again, random set of 3D. In this case, I think they make it 3D by, using the width of the image, and use a pre-trained network on a random slice again of each of the 3 or 4 and predict on that. And that even, again, if you do it on just a random slice of given thickness, you're not even sure in that case that necessarily the tumor exists in the part of the slice that you have taken, right?
Yeah.
Because there is no indication, there is nothing, because you haven't done what Steve was talking about of segmenting, that you just taken it, and in fact, 4 random slices from each of the 4 types and predict using 3D pre-trained network, and that amazingly leads to a result of 0.6. I forget now what 0.65, 6 something, and so on, which is pretty incredible. But in the process of going there, I had a question before I moved off from that topic of 3D. I assume, and I just wanted confirmation that just like you want to size the X and Y of all the images going through a 2D convolution to be the same in a batch, I assume the thickness has to be the same for 3D convolution for all the images that you're passing through. That's true?
Ideally, yeah, you want that. Yeah, so you want, right, I think that's what we did in our CT project. Did we resize?
Or is that not?
Yeah.
I haven't looked at the code. I can easily check it, but I just wanted to ask you, since you have experience in this, whether my assumption that you would have the thickness also be the same, much like you would make X and Y the same, whether that's true or not.
Yeah, X and Y the same size, but and thickness also the same size, but yeah, sorry, X and Y, so has like let's say 128 by 128. So let's say we use cropping. We crop the brain and then we resize it to resize to 128 by 128, and then we just need the thickness to be the same in the Z. So let's say we pick a thickness of 1, but the number of slices in Z can be different. Like say it can be like 64 slices or 128 slices, but as long as they're the same thickness, and we can just have like a global average pooling layer that will take care of varying number of slices. You see what I mean? So you need some resizing to make the thickness the same, but the number of slices might be different, and that's fine.
But then you would need to understand the thickness to slice conversion for every image and apply it appropriately to when you're creating the batch, though.
Yeah.
Because that varies depending on the type of image, right?
Mm-hmm.
Not just type, depending on the particular image taken for the particular patient, because it will vary from patient to patient, correct?
Yeah. Mm-hmm.
Which means so if you're talking flare images, then what you're saying is if you do this approach of thickness being the same, but slices could be different because different number of slices add up to the same thickness, because that can be changed or that will change from MRI image to MRI image, correct?
Mm-hmm. Yeah.
So you'll need some processing in your pipeline to understand that from the metadata and fix it.
Yeah. Mm-hmm.
Is that what you have to do?
Yeah, you would need to prepare your data. Yeah, there's a lot of data prep here, just mostly image, understanding and resizing the images and cropping. So it's basically crop and resize, but doing intelligent resize.
Right. But what I'm saying is my understanding right that in the Z dimension, because the thickness of let's say patient 1, patient 2. So patient 1 could have a flare image with certain number of slices per millimeter of thickness, right? Yeah. Which we will get only from the metadata.
Okay. Mm-hmm.
Right. And for patient 2, the number of slices per millimeter of thickness could be different.
Okay.
Therefore, because it could be taken at a with a different setting on the machine, blah, blah, blah. Therefore, if we want to make thickness the same for patient 1 and patient 2 in the Z dimension to create a batch, then is my understanding right that you would need to know the metadata of the setting to, of the thickness to slice correlation or, conversion in order to make the thickness the same for the entire batch for patient 1 and patient 2 in this example.
Yeah, so you um, so basically, yeah, so let's say patient one was 1 millimeter, right? Z thickness, and patient two was 2 millimeters. Um, so and patient two is 2 millimeters and has 10 slices. So then if you make it, I'm just trying, if you make it 1 millimeter, does it mean 20 slices? Maybe. So yeah, but you do this before you make your batch, right? So you do all your
Correct,
conversions
correct.
first.
Yes,
Yeah.
yes, correct. But what I'm saying is you would need to do that pre-processing to equalize the Z
Yes,
dimension before you create the batch. That's
right, yeah,
my understanding, and I just wanted to
right,
confirm whether that's
yeah. And
okay.
some of, yeah. I just wanted to share one more so this Monai tutorial, this is like they are using 3D classification, um, and they have a small data set to play with. It's I think it's just from this website in the UK. Um, it's what was the classification task was just oh yeah, just to say from the MRI, just say if it's male or female. Okay, and they have a collab, so we can just run it. Um, yeah, and they already have it in Nifty, but see they've done all the pre-processing, I think. So this one is. So in this case, I guess for the collab, they just did, they made everything 96 by 96 by 96. Um, and they have like a training data loader and, like basically the training loop setup in PyTorch. Let's see. Oh, they didn't show their results. Okay. Maybe for next time, I'll try and run this myself and see how it does. But yeah, this is what just how did they have a pre-trained dense net? Let me check. So, okay, they do release dense net like dense net 121 with um yeah, I was trying to see how many like but I think it just looks like they don't have like Flare T1. They probably only have T1 or something like that. I'll run this for next time, or I'll just put it, if as soon as I run it, I'll just put it on the Slack channel. Yeah, I see. They only have T1s. So this is like Srinivas, what you were saying. Like like you could have a T1 model, Flare model. So this is like a T1 model that and they have some augmentations, um, like say around rotations, and I'll have to check what the scale intensity is. Uh, because in the, like we were discussing last time, in the CT, zero means water, and minus 1,000 means air. But here, that it's not normalized. Like, so in one scanner, so the black part is water in the MRI. So these are the eyes. So then the eyeballs is some liquid. But you take the same person, you put him in two different scanners, and the intensities will not be the same. So there is always some normalization. Like, so he has some, either 0 to 255 or 0 to 1, or yeah. Yeah, and I think from one of the other competitions we saw, like I don't know if anyone's done it yet, is um, we have these slices, right? So you have a 2D CNN, but the Z part is done with a LSTM or some sequence model. So you, but I don't know how to set that up. Can probably share a link
Yeah,
from
it's
that.
almost like one suggestion I'd seen. I haven't obviously done it yet, but one suggestion simple that I've seen is to say, think of it as a sequence to sequence. And so you kind of put the Z-axis along your LSTM sequence length dimension, if you understand what I'm saying. Like, make the LSTM and then have that predict the hidden layer like you're doing in a translation. And then on the other side, make the prediction be the last output, giving it a 0 or a 1.
I see.
But, obviously, I think last week, what you kind of shared or pointed to, the weights and biases person, I forget, Anurag, I think his name is, I forget, Thakur. He has either done or was hinting at doing it that way or attempting a baseline implementation. The other baseline suggestion that I had seen, just to share baseline, since Steve was also pointing to notebooks that had implemented baseline, but this suggestion I saw that I thought was simple enough that I might try it as a first step is, you could potentially convert, see, we have a label per patient, correct?
Yeah.
Of 0 or 1. But you could convert that to label per entire image set. You see what I'm saying? You could convert it to every image of every image type, and every image in every image type has the same label, right? And then predict on all of the images, and then use, just because now you've made a multiple mode and all that collapsed into just a bunch of 2D images with labels. You see what I'm saying?
Do you mean
that
like
you have
label,
Claire, you have T1.
Do you mean label per slice or like a label per volume?
Yes. No, label per slice, because per slice per patient. So a patient has a 0 or a 1, correct?
Yeah.
Eventually. So you take that label and you propagate it in a sense to every image corresponding to that patient of whatever type.
Okay.
Right?
Is the problem not though that if it's true that you can only really predict the MGMT from the actual tumor, if you start labeling loads of images that don't have the tumor on it, saying that their MGMT equals to 1, is it not going to cause you problems? Like, do you not need to restrict it?
Yeah, that's why it's no, sorry. Could you repeat that, Steve?
Are you talking about like, so you take every single slice from the DICOM and you train each one separately and you give it the label of 1 or 0 depending on if that patient has 1 or 0?
No, don't train separately, meaning label every slice, which a slice is a 2D image, right?
Yeah.
And again, this is a thought that somebody had, and I thought, okay, that seems simple enough and might be worth a shot, just to see what you get. So every slice of every type of MRI, you give it the same label as what the patient has, right? So you will get, right? So you'll, and then train using all of the images, right, for all the patients. Now, that your training is basically a 2D classifier problem, because you've completely eliminated the types of MRI, and you've completely eliminated the third dimension, because you're doing it per slice, per patient. But the label remains the same, whatever the patient label is, 0 or a 1. And
yeah,
then,
but what I'm saying is the fact that yeah, like I think to tell if you've got MJ or MGMT, is that not just from the tumor? And so like if you start
Yeah.
training on every single image and like labeling it as one when there's no tumor there, is it not gonna like just completely break the
Yeah,
model because of the
that's yes, that is true. The only true solution that fixes it is if you do segmentation. If you don't do segmentation and you use the images, any other approach that you come up with which doesn't actually segment your pre-segment your image, which you talked about in the beginning, has the same problem.
Yep.
So so far I've only seen non-segmentation solution that people have posted. As I said, I haven't looked at the top submissions that people have made and how they've done it. But the ones that you pointed to and a few others I looked at, all of them have not used any segmented data.
Yeah.
And if you're not using the segmentation data, then you have the same problem that I admit, yes, I agree wholeheartedly that the problem you're saying exists with this approach, but that's why it's a very rudimentary baseline approach. But I'm also pointing out that the same problem exists in any approach which doesn't do segmentation.
Yeah, sure. But if you give it like all of the images as one for a patient, and yeah, so like you give it like it all together or whatever, like at least the tumor is in some of those, and so like it might learn to sort of detect which ones have the tumor and sort of say, yeah, like the label is one from these. Whereas if you give it like individual labels by themselves, then some of those won't have the tumor in them at all, but you're labeling those as one. The other thing I'd seen as well, like at the start we'd talked about, yeah, people have used like basic CNN and just sort of chosen images at random, and they were getting like 0.6 scores. Yeah, suppose I'll just share this a sec. Somebody's done this other notebook simulation, and like they say that basically if you just like choose random values, so like this isn't using the images at all, it's just creating random values, and like with the metric that the competition is using, it says that if you just use random values, you should get a score of about 0.65. So
yep. So and I was coming to that because that basically says that the CV is what is important. That was I was going to get to that as my next issue or question.
Yeah, so like these networks, the CNNs that are sort of choosing images at random and training and predicting on them, they're actually getting sort of worse than if you just did it at random. So,
right, but that leads to this question, right? Which is the important thing there that I took away is because the if I recall and I forget now, the private test data set is 87 images, if I recall correctly. And, we have, I think in the training set, 585. So if you split, 20% of it or something, you may get like 120-ish number. So your CV is probably a little better than your 87, right? So in other words, the comment and everything there seem to, and by the way, there's more discussion regarding this. There's another related question that I'll come to in a minute, but sticking with this problem that you identified, Steve, the comment or what I took away from it is that you need to rely more on CV than necessarily what your leaderboard provides. And by the way, the public evaluation thing is going to be about 5x in total. So something like, I would say 400 total, of which 87 have been provided already, right? So the remaining, 500 minus 87 or in that ballpark is what would be in the private data set that we will eventually get scored on when the competition ends. So if you kind of focus much more on the leaderboard, which is what I took away from all the discussion, then you may not actually be doing the right thing. Is that what you understood, Steve, or is your takeaway different?
My takeaway was, yeah, basically, if you're not getting higher than 0.65, you're effectively as good as random or whatever. So, but yeah, like as you say, the public leaderboard is very small, and there's actually a discussion as well about people saying that, yeah, it'd be possible to like do a complete leaderboard probing of the public thing and get a score of 1. I think they said it was like 17 days. You could, if you do 5 submissions a day,
Right.
you can completely predict the public thing. And so, yeah. So the public leaderboard score is probably not a good one to go off because people will be cheating on it.
Right.
Or probing.
So I took away from that CV, as Rekil used to say, the most highlight, the importance of getting a good CV test or cross-validation set that is really robust, and your performance against that is what you ought to be most worried about. Would you agree with that?
Yeah, I think so, yeah.
And which lead me to this other observation that I saw multiple people post, and I had a question or something we should discuss, is this metric for this competition is I think AUC, right? And one of the things that people were posting is they were using loss in some cases as a metric they use rather than AUC, because they were not seeing good correlation between their AUC scores they got on some of the runs to the leaderboard. And given what we just talked about, I was kind of more of the opinion that we ought to, stick to AUC scores in your CV set as being kind of the sole metric that you go by, not so much what you get when you submit to the leaderboard. And AUC scores meaning the same metric as what you care about, rather than using loss. Do you concur, have different opinions? Anybody have comments?
No, I just thought about what I think just like what you were saying earlier, like cross validation, but yeah, I don't know what is better. Like maybe a cross validation AUC, right? That might be
Yeah.
Yeah, I can't think of any advantage of like cross validation loss, but I can read those posts, but I don't.
Because, again, I'm referring to way back to what I recall from past AI, Jeremy saying, you ought to really not go off loss when you're trying to decide. And you have to look at the metric really rather than the loss. And given what we just had a discussion about, your leaderboard score is not necessarily indicative of your goodness of your model, given how small it is, and you could potentially overfit or even probe in order to get a really high score. Then just going off leaderboard can lead to other problems, I thought. So that's those were some things. Anyway, to finish the thought on that baseline, yeah, I agree with you, Steve. It's just it was more to see whether it leads anywhere, and it just said then in the prediction phase of what you do there, you just predict per patient and then take the mean of all your predictions to see whether you get anything in that approach. But it's very similar to what taking random slices or any of that kind of stuff really does. The couple of things I was pointing to, and I'll post the links, but if I'll share my screen just to show folks, let me know when you can see it.
Yep.
Okay, so this is the stuff that I was talking about, transfer learning for 3D medical image analysis, MedicalNet.
I see. Okay.
And you get, and you get the ResNet 10 to
nice.
so you could potentially go with that, right?
Is this?
You can see though what they talk about for pre-trained though.
Is this only for segmentation? But no, not
this is primarily for segmentation, is my
okay.
Recollection. But again, I have to look at it to see whether there's anything which somehow limits you from using it for. And there's a bunch of other stuff that they, right, this is one. And then there's also this other stuff I found. There's a medical zoo for PyTorch. Again, it's a segmentation library, but UNet, our old friend, right? And then a whole bunch of other ones that I haven't heard of.
Yeah. Oh, nice. So he's so these are MR brains from different competitions. So he's loaded them or done some, and they are, see, you have Flare, blah, blah, and somehow they.
This one has all four that we are dealing with, right?
Mm-hmm. Yeah, I think we are. It's a similar competition. The Mikai Brats. That's the one.
Yeah, the Brat one seems to be kind of somewhat the second part that Steve talked about, or similar to the second part. It's not exactly the same one, but it's similar to that.
Okay.
It's more segmenting the portions of the brain tumor and stuff like that, or the lung tumor or the liver tumor or whatever. Right. And while we're on the subject, I'll also point to another, for me, because this is Mehul's bailiwick, but I'm still trying. So there's a whole series of posts. Can you see my screen now?
Yeah. Oh, can you see?
So there's a whole series here on 3D medical imaging with PyTorch.
AI summer. Okay.
See, there's a whole bunch of stuff.
Can you share this link later in the Kaggle?
Yeah, I'll put it in the chat as well. And then, Mehul, I think you already shared, but something, and this is around the MRI stuff, video on that. And this one I thought is actually would be useful. Is there's a whole series on 3D convolutional neural nets. Of course, it's related to lung cancer detection, but because I haven't done 3D convolution, there's a whole series of stuff here about, and especially the resizing part is something that I was in pre-processing, was something that I was interested in understanding. So that's something else that I thought would be useful to go through. So I'll post these 3-4 links once we are done, but that's essentially what I spent things similar to Steve, but I haven't yet got into duplicating any of the code and getting the stuff working, which I plan to do this week.
I'll try for next week. I'll try and share an example of the resizing, like maybe I can take that notebook which talks about like the flare, the orientation of the flares, and try to bring all the flares in one orientation, for example.
Yeah, because do I have that here? Well, let me quickly see. I know where. If you give me a minute, I'll take you to where the guy shows. And maybe the images are removed because there are some empty images, Steve. So that may be the ones that got eliminated. And then, sorry, give me a minute. Let's search for what I'm looking for. This notebook to export all series planes. This is the one that I was mentioning about. This is a quick notebook that he points to that helps you determine what plane the data is, and then he exports it to the CSV file, even within a particular. So each of the stuff is different, even within a type of image, and then you can just export it all to the same CSV file and can look at it. Similarly, you also have another. He also has something for heightening the contrast that I thought would be useful too, of images in order to allow your CNNs and other stuff to find related things. See this voilet again. You may be able to explain more about what it means, but this seems to be able to highlight some specific regions. Is that what it's used for, Mehul?
I've noticed in the code that I took that, like a lot of the people, they apply that if they can. I think there's like some setting in the DICOM image that says if you can do it. And, like a lot of the DICOM to NumPy or DICOM to PNG code applies that thing.
Yeah. To make LUT. I don't know what. I guess now at least. And this, determining MR image planes kind of is what is this thing, the three planes, and then see, he says, for example, here that in some studies the flare sequence is in coronal and in the sagittal plane in other studies. So, which means that even your images within the image similar type can be of different orientation, which can, yeah, see, first study flare is coronal, second study flare is sagittal. And then, by the way, I mean, the sizing, I guess if you use pre-trained and you resize, that should be okay, but sizing is different. Anyway, those are some of the things that I was playing with. There's a bunch of related and extremely precisely targeted papers, but you know, it's like too much data to go through. There's like a bunch of them we talk about. The radiodynamics in brain tumors, specifically focused, for example, on identifying the MGMT stuff that we are after. So if I scan any of these and find anything extremely relevant, then I'll post that as well. Okay, that's all I had. I guess we need to look at the secondary competition to see whether we can, you know, as Steve said, just use data from that to learn the segmentation using the pre-trained segmentation models that I was pointing to, and then use them to predict, and then use that output of that prediction. So you would use the output of that to, you'd need to, how do you need to generate the mask from it and use that mask to then help determine the inputs to your classification pattern. Is that what you're thinking, Steve?
Yeah, basically I was thinking, yeah, like there seem to be quite a few other sort of competitions where they're segmenting to find the tumor. And so, yeah, like if you were able to create a model or take a model from one of those, and then you would just like stick all of this training data through that model to predict which slices are showing the tumor. And then you would only use them to put those into your second model to predict the MGMT. So yeah, like hopefully all of the slices that you'd be putting into the model would be the ones where the tumor's shown, or like even better if you can segment the tumor out of the image, so as you just cut it down to like that region of the slice that has the tumor in it.
Right. So almost the mask, the segmentation mask. I mean,
so
the picture corresponding to the segmentation.
Yeah, so like those other data sets, they have the segmentation masks for them, but yeah, like they are all just whatever MRI scans. So I don't think it matters that they come from different patients or whatever. As long as you have a model that's good at identifying tumors, then you should be able to apply it to this data set. So it doesn't really matter that your model hasn't trained on this data set for identifying the tumors. And then you just use this data set for identifying MGMT once you'd sort of narrowed it down to which bits of the slices have the tumor in them.
Yeah, interesting. Kind of two steps.
Arto and Gautam weren't here last week or whatever, so is it worth like saying to them about how we were sort of thinking of proceeding with this, given that it's like an ongoing competition?
Sure. So what Steve is alluding to, Gautam and Arto, is we were previously just competing in Finnish competitions so that we wouldn't run into any issues of sharing code, blah, blah, blah. But as Steve said, there may still not be a problem if we don't share code. But the other thing is, if we have only 5 people or less and or we post any code we share to the public forums in Kaggle. And as we saw, we may have 6 or 7, but people drop off. They aren't continuing to participate and or engage. Then it really doesn't matter. And at least both Steve and Mel were very interested in this particular competition. So we kind of chose an active and ongoing competition. This competition is currently active and is going to be active, I think, for another 2 months, Steve.
Yeah, I think so. Yeah.
Is that right?
Yep.
Yeah.
That.
So we are kind of participating in that, and we could, as long as we share only within 5 participants and or then there's no issue with respect to Kaggle. So that's kind of where we ended up with respect to this group and ongoing participation. And so we had our first discussion. I might have forgotten to post the recording. I'll do so today for both, but that's kind of the background, and we stuck with this one because it's current. The couple of people who are interested, and we then agreed that we will go ahead and just participate in this as an ongoing competition. And as long as we share code with 5 or less participants as a team, then that should allay the concerns. And that matters again only if we actually share code. So that's kind of the background. And we spent last week just kind of even basically understanding what the competition was about. And as you can see, we are still kind of trying to figure out the various data set related issues and how we go about making progress, or how should we even tackle the problem.
I see. I like the idea to participate ongoing competition. And as for this particular competition, I'll probably won't participate it. So if you would want to form a team, I would rather not join it, because it would be kind of I don't think I will have time to do some meaningful contributions to this. So yeah, I'm not sure how this should work.
Yeah, no, that's fine, Natu. I understand. I mean, interests vary, so not an issue. I mean, you can still join the discussion. That's not a problem. And as I said, it's not we just were participating in Finnish competition to be kind of like very precisely follow the rules. But I read the rules again, and so did Steve. And, the rules only apply if we actively share code, and that is when we form the teams, and the team sizes have to be less than 5, or up to 5. So I don't think we are in violation in discussing anything and in showing code or stuff unless we actually share code. And even then, sharing is allowed as long as you again post anything that has already not been shared on the Kaggle forum. So I think we are in the clear, even if more people join, as long as we comply with those. So just wanted to kind of highlight that we are participating in an ongoing competition, and B, these are a couple of the rules that we have to abide by. But it's perfectly fine. Understand. May not be interested in this competition.
Also, as well, it's not as if we're sort of a team or whatever yet. So each person, if they want to, they can join the competition, but they're not in any teams. They're just joined by themselves, and it would only be you only need to sort of form into a team in the last week or 2 weeks or whatever of the competition if you want to. So yeah, like it would only be at that stage if there's like sort of 5 people who want to join up that you would. So you can like sort of do as much or as little as you want.
Yeah, I see. But if you would want to share some code with not publicly, but within this group, you would need to form a team, right?
Yeah,
at
if
that
you need to
point,
share any,
then
if you need to have a team and share privately, then yeah, you would need to do it outside of this group probably.
Oh, I see. Yeah, nice.
yeah, so that's kind of the background, if you will. Because interest was waning otherwise, and maybe people just want to come and talk about whatever competition they are participating in. That might be a completely different approach. But even when I asked about and solicited stuff, maybe it is people are busy with a variety of things, and it's after all relief from COVID, and people are getting out more and having to do more and stuff. So in that sense, and it's summer after all too. So all that I was kind of considering, even necessarily not continuing and shutting down the channel and having somebody else maybe do it. But then Steve suggested, hey, why don't we morph it and see whether it continues for a while longer, and we'll give this a shot and see if enough people are interested. If not, then we can end the channel and do the.
Yeah, I would guess when summer is over, we will have more people again, because yeah, for me, definitely summer is part of why I was much less available.
Oh yeah.
During
last. No, that's part of it. Also, like I said, COVID is over, at least in some parts, even though it's coming back, but hopefully it will continue to stay. Then that, prompts people to move, travel, a lot of that kind of stuff too. So some of it is anticipated. And I always knew that, in this case, because you have to kind of actually do something, and also not every competition is of interest to everybody. So I think there's that element to it too. Cool. Gautam, any comments?
Hey, no, yeah, like, yeah, it's similar to Arto. I'm mostly here to just learn about stuff. I don't know how much I'll be able to actually contribute, but yeah, I'll try as much to contribute to the discussion. And yeah,
yeah, I think even listening in, you learn our pointers to variety of things and stuff. So welcome to join in when you have the time.
Yep, sure.
Okay, great. Thanks everybody for joining, and I'll post a bunch of these links and stuff a little later.
Thank you.
Okay, cool. Cheers.
Thanks.
Speak to you next week then.
Bye.
Yeah, bye.
Yeah.
Bye.